So in this lecture we will introduce the product principle. And so one way to motivate the product principle is with the basic counting problem. How many outfits can one make if you have 5 different shirts and 4 different pants? And assuming, of course, you don't plan to go topless or without bottoms. And so, of course, let's make our shirts. So there's shirt 1, shirt 2, shirt 3, shirt number 4, and shirt number 5. Yes, I realize these look a little funny, but, well, I'm not an art major after all. Now let's draw the 4 pairs of pants. Let's say you've got black pants, blue pants, green pants, and red pants. Well, you have to pick at least one shirt. And so suppose you picked a black shirt. Then you have to decide which pair of pants. So suppose they picked the red pants. And that's one possibility right here. The black shirt and red pants. But of course you could have also picked green pants, or blue pants, or black pants, and so on and so forth. So we see that there are 4 different outfits where you pick the black shirt. Likewise, in the same way, if you pick the red shirt, there are 4 different outfits, and so on. And so for each of these rows, you could actually fill it in with 4 different possible options. And so there's 4 each. And so we see that we add 4 to itself 5 times. And that's the same thing as 5 times 4. There's 20 different ways. So theoretically, I'm actually using the addition principle right now by breaking up the set of possible solutions into 5 subsets that are disjoint and counting each of those cases separately. But it turns out we could have done this much more quickly if we just used multiplication. And so the idea behind the product principle is to use multiplication to solve your counting problems. So in order to talk about multiplication, we have to talk about products of sets. And what is a product of set? Well, in this class it's called the Cartesian product after Descartes. Given 2 finite sets A and B, A times B is the set of ordered pairs, where the first coordinate is from the first set and the second coordinate is from the second set. In fact, we can actually talk about more than just 2 sets. Given a finite set I and a bunch of finite sets, 1 for each element in I, you can form the I-fold Cartesian product. And the idea is that a point in this Cartesian product could be viewed as a sequence. So given an element in this set and given an I in your index set, you've got some sort of ith coordinate, and the ith coordinate lives in the ith set. And so this is very abstract, but it's the appropriate level of generality to talk about the product principle. And so, for example, if I is 3, then what are we talking about? We're talking about a Cartesian product of 3 sets, A1, A2, and A3, which basically just means triples of elements. The first coordinates in the first set, the middle coordinates in the middle set, and the last coordinates in the last set. But you can replace 3 with n, and you're talking about Cartesian products of n sets. But sometimes you don't want the numbers 1 through n, you just want an arbitrary finite set I, so this is the level of generality we're going to use. So suppose we changed our counting problem that we started with. Suppose instead I want outfits where I have 1 of 3 hats, 1 of 5 shirts, and 1 of 4 pants. Then we see that we're really looking at the set H for hat, times S for shirt, times P for pants, where H is the set of hats, S is the set of shirts, and P is the set of pants. And so when you pick out an outfit, you have to pick out a hat. It's the first coordinate. It goes on top of your head, not on your foot. The middle coordinate is the shirt, because that's in the middle of the outfit, and the last coordinate is the bottom of the outfit, so the pants. And so we see that the answer to our counting problem is the number of elements in this 3-fold Cartesian product. And so how would we solve such a problem? Well, we have the product principle. If your index set is finite and each of the individual sets is finite, then the number of elements in this Cartesian product is just the product of the number of elements in each coordinate. And if that's a little too abstract, well then if I is just the integers 1 through n, then the number of elements in this n-fold Cartesian product is just the product of the elements. So in particular, in our case, the number of elements in our triple product is just the product of the number of elements in each one. And of course, that means 3 times 5 times 4, which is 60. So there's 60 possible outfits in this case. And in combinatorial applications or in basic counting problems, the product principle arises whenever you are studying a problem where you have several choices in sequence to make, and each of the choices is independent and does not depend on previously made choices. In those cases, it usually turns out you can rewrite your set as a Cartesian product and then apply the product principle. As an example of the product principle, let's consider the problem of computing the number of strings of length n, where the string has to use the symbol 0, 1, 2, 3, up to k. It's worth, of course, pointing out that n and k are both positive integers here. And so I guess as an example, let's pick n equals 2 and k equals 3. You will find quickly that these get a little too big to do in general. So what do I mean by a string? It's just a list of numbers. And for k, so I'm allowed to use 0, 1, 2, or 3. And so you have 0, 0. That's a string of length 2. Same with 0, 1, 0, 2, and 0, 3. You also have 1, 0, 1, 1, 1, 2, 1, 3. 2, 0, 2, 1, 2, 2, and 2, 3. And finally, this one. It's worth pointing out, we do not see 0, 4 because 4 is bigger than 3, and we do not see 0, 0, 0 because we're insisting that the length is 2. You only have 2 symbols. And so the way I set it up in this case, we see that, well, you can pick your first symbol in 4 different ways, corresponding to the 4 different columns here, and you can pick the second coordinate in 4 different ways, corresponding to the 4 rows. So we see that the answer is 16. But of course, we want a more general formula. And so it's worth pointing out that this set of strings of length, let's say nk, so strings of length n using the symbols 0, 1, 2, 3 up to k, could be viewed as being a Cartesian product of the integers 0 through k times itself. So this first set corresponds to the first coordinate, or the first symbol in your string. The second set corresponds to choosing the second symbol in the string, and so on. And how many different times does this set have to appear? Well, it has to appear n times, because the idea is that you have to pick n different characters in order. Order matters for this problem, but when you're picking the ith letter does not depend on the previous choices, so they're all independent, and so it turns out that this set is essentially the same set as this Cartesian product. I should put quotes here because, well, it's not exactly equal, but we'll discuss that at a later lecture. And so then we see that the number of such strings is just the product of the numbers from 0 to k. And we're going from 1 to n. which is also known as k plus 1 to the nth power. And that's by the product principle.